Today we're going to talk about conservation of momentum. And the first idea we have to understand is this idea of conservation, because most people have heard that word before, but we have a very specific meaning in physics. In general, when you hear about conservation, you're probably thinking along the lines of conservation in the environment, right? We're trying to conserve resources, conserve energy, that kind of thing. And the meaning is very similar in physics, but with a slightly more specific idea. So conservation simply means that something stays constant. Something stays constant. It doesn't change. The value does not change. So when we're talking about conservation of momentum, that means that the momentum will not change throughout the problem. So how do we get to this idea? Because we've seen momentum change. We've hit a ball, right? And we've seen the momentum change. We've looked at some carts probably by now, and we've seen that the momentum has changed of those carts. So how does this idea of conservation of momentum work? Well, let's remember our impulse change in momentum equation looks something like that. And we know that impulse is just force times the change in time, and change in momentum is just the final value of the momentum minus the initial value. And this holds true. And this is still going to be true even with conservation of momentum. Where it gets interesting, though, is what if this force is zero? So if our net external, and this word external is going to be really important, if our net external force is equal to zero, then P final minus P initial equals zero. Then our final value of momentum equals our initial value of momentum. This is the definition of conservation. So momentum is conserved. Okay, the total momentum of the system doesn't change. And that's important. And we're going to talk about why we're using that word total. The total momentum of the system, and that's another important word, does not change. So, the key part to remember with conservation of momentum is that this only applies when there is no external net force. So think about when we've seen momentum change. When we hit a baseball, so we apply a force on the ball with the bat. When you kick a soccer ball, so you exert a force from your foot on the ball. In all of those cases, we had a net external force. We're going to be looking at those, and we're going to be changing them up a little bit so that we only look at situations where the net external force is zero. So we're going to use this idea of conservation of momentum to solve two different types of problems. The first is going to be an explosion. And don't get too excited. We're not going to have fireworks in class, okay? An explosion simply means that there are at least two things that start together, but come apart. Okay, so you had two, for instance, you might have two carts that are together, and then a spring between them pushes them apart, and they explode, okay? The other time we're going to use conservation of momentum is in a collision. And this is exactly what you think about, for instance, two things are moving toward each other, like two carts, and collide. They might bounce apart, like as in maybe two carts, right? They hit each other and collide, each collide backwards, or they might stick together. So think of a linebacker tackling a running back, right? They grab on and push them to the ground. So they were running apart, and then one grabs onto the other and pushes them down. So that would be a different type of collision, okay? Now, let's get this idea of a system down, because a system, we haven't really looked much at systems yet. So a system is simply a group of objects we will focus on. So this is the group of objects we are focused on. So for instance, when we talk about net external forces, and we talked last semester about how you cannot apply a net external force to yourself, right? You can't. So for instance, when you walk, the floor exerts the force on you. Well, that's because you are different than the floor, so the floor can exert a force on you. But your arm can't exert a force on your leg because that's all part of the body system. So what we're going to do now is we're going to change up the problems we've been looking at with change in momentum problems. And we've said, well, if you have a ball and the ball hits the bat is exerting an external force. Well, what if instead we looked at the ball-bat system together? The ball can't exert an external force on the bat because it's part of that bat system. And the bat can't exert a force on the ball because it's part of the system. So in total, the momentum of each of those objects is conserved because they cannot exert a force on each other. So that's what we're really looking at when we talk about conservation of momentum. Now we're going to look at explosions first because they're a little bit simpler, because in most cases we're going to start out with an initial momentum of 0. So let's see what we mean by that. So let's take a look at our system that we have here. And we have a person-boat system, and they're at rest before the person jumps off the boat. You can see they look like they're going to do a little dive here. So when I talk about the person in the boat, I'm going to say that the initial velocity of the person is 0. Therefore, the initial momentum of the person is 0. And I use a lot of subscripts with this. So you could change that to V initial of object 1, P initial of object 1. It really doesn't matter. I like to use person. And then I know that the initial velocity of the boat is 0. And because the boat's velocity is 0, I also know that the initial momentum of the boat must also be 0. That means that the initial momentum of the total system has to equal 0 because the momentum of each of the parts is 0, right? If I take this plus this, I still come up with 0. So the initial momentum of the system is 0. And that's why starting with explosions is pretty easy, because you're usually starting with a initial momentum of 0. That means if I were to ask you what is the total momentum of the person-boat system after the jump, well, when I look at this system, there's no external forces, right? The person's going to push off on the boat, and the boat is going to push off on the person, right? That's Newton's third law. Newton's third law says if the person pushes on the boat pushes on the person. But those are internal forces to the system, so I know that momentum is going to be conserved. Therefore, since momentum is conserved, I don't have to do any math. I know that the final momentum of this system has to be 0 as well. No calculation needed. But that's going to allow me to do some calculations. So for instance, if I know the boat has more mass than the person, after the person jumps, I know which one will be moving faster, because this person's momentum, so this is the final momentum of the person, and this is going to be the final momentum of the boat. Those have to be equal, just in opposite directions, because I know the boat's going to be moving. And I know the person's going to be moving. So they're each going to have momentum. But they have to have exactly the same momentum, because that has to add to 0. The only way to have a final momentum of 0 is to have both objects moving is to have these two momentums add to 0. So that means the final momentum of the boat plus the final momentum of the person has to add to 0. That means one of these has to be negative. And I can see by looking at it that the person's going to have a negative velocity just because it's going to the left. That's our convention. So I know that the final momentum of the boat is going to equal the negative of the final momentum of the person. So whatever it is, whether it's 50 kilogram meters per second or 100 kilogram meters per second, it doesn't matter. One's going to have, say, 100 kilogram meters per second of momentum. The other's going to have negative 100 meters per second of momentum. That's just the way it has to work for those to add to 0. So let's think about what this means for a velocity. And you can kind of reason this out a little bit first. If the person has much less mass, don't they have to have more velocity then to make up for the much bigger mass that the boat has? So if the boat is much bigger, much more mass than the person, whichever has more mass is going to have less velocity. And you can think about this. What if the boat was really, really heavy? Like you're jumping off a cruise ship. Wouldn't that be nice? Right? You're jumping off a cruise ship. The person gets tons of velocity. The cruise ship barely even notices. So the cruise ship has very little velocity while the person has a bunch of velocity. They have to, because they have to make up for the fact that they have so much less mass. So let's go ahead and let's try this with some numbers. So what we've got here is we've got a situation where we said the boat has a mass of 60 kilograms and the person has a mass of 45 kilograms. And the person jumps from the boat with a velocity of 5 meters per second to the left. Now notice that means if they're going to the left, we know that their final velocity has to be negative 5 meters per second. We want to know what's the resulting speed of the boat. So the first thing I'm going to do, and I'm always going to make sure I do this, is I'm going to figure out, well, what is the initial momentum of the boat? We don't really say in the problem. If the boat has a mass of 60 kilograms, the person has a mass of 45 kilograms. We're given the velocity of the person after they jump, but we're not given any information about the velocity before they jump. So we can assume, we're going to assume, because we don't really have a choice, is we're going to assume that the initial velocity of the person is equal to 0 and the initial velocity of the boat is equal to 0. That allows us to state that the initial momentum of the total system, the person-boat system, is 0. Well, if that's true, then by conservation of momentum, we know the final momentum also has to be 0. But the final momentum is made up of the momentum of the person, so this is the final momentum of the person, plus the final momentum of the boat. Well, remember that momentum is just mass times velocity. So the final momentum, which we know is equal to 0, has to be equal to the mass of the person times the final velocity of the person plus the mass of the boat times the final velocity of the boat. Well, I know a bunch of these. So I know that 0 must equal the mass of the person is 45 kilograms. And the velocity of the person is negative 5 meters per second. I know the mass of the boat is 60 kilograms. I just don't know the velocity of the boat. And sometimes like I did there, I probably shouldn't have done that. I should have put the final velocity, so FB. Well, the only thing I don't know here then is the velocity final of the boat, so I can go ahead and solve for that. So go ahead and hit pause here and see if you can find out what the final velocity of the boat is, and then come back and check it. All right, hopefully you did your math, did some algebra, and you found that the final velocity of the boat is going to be 3.75 meters per second. And I know that's going to be to the right because the person was jumping to the left. I see that the person has a negative velocity. That's how I know it's to the left. I found the boat to have a positive velocity, so I know that's going to be to the right. So that's how we're going to set up all of these explosion problems. So we've got some for you to practice with. So go ahead, take a look at these, list out your variables, find your masses. Instead of using mass of B and final velocity B, you can always use M1 and M2. Just be very consistent. For instance, with problem 1, we have a 10 kilogram cannonball and a 1,000 kilogram cannon. So if you're going to use 1 and 2, then make sure you label it like cannonball is object 1, cannon is object 2, then you won't get lost with your subscripts. All right, try those problems and good luck.